Short lesson in tropical seagrass, just to make sure we're all on the same bits of information. I'm going to go quickly through the two major monitoring programs and then drop back to a couple of our research projects, risk mapping, connectivity dispersal and informed fisheries. Now these are not specifically NESP projects, but some of the NESP work underlines the information we have and has been very important to us. So just to put you in the picture then, we're in the tropics, not the temperate wild, so the seagrasses, and this is just a map of biodiversity through the Pacific. Note that we're in a very important place in the seagrass world. It's pretty well the seagrass triangle, very similar to the coral triangle if you like. The difference is though that, it may not be that different, is that we don't have a lot of information for some of those really important Asia, Indo-Pacific seagrass areas. There's almost no spatial information coming at the moment from places like New Guinea and West Papua and further north. The advantage we have in Queensland is that Tropwater has that seagrass group of 20 or so scientists in Cairns. And we have a long history of working on tropical seagrasses going back to the very, very early 1980s. And we have really good data sets from that. We're probably the biggest and longest running seagrass group in the tropics in the globe outside at least the Caribbean. We'd like to look further north. When I say there's been no spatial information from New Guinea in recent years, we did have a NESP project in round one. Alex Carter's here, who managed to map the seagrasses in the southern part of New Guinea, northern part of the Torres Straits. That's the first bit of information we've had from New Guinea waters in the spatial sense for some time. There is some research going on in that part of the world, but very little spatial information. When we did the Atlas of World Seagrass in 2003, there was also only about 4 square kilometres of seagrass included in that atlas from the Pacific region. That just showed the lack of information for tropical seagrass species. We're facing sea level rise in the next few years, and right through the Pacific we do not really have a good idea of what seagrass is there and how much we're likely to lose as sea level rises. Unlike the Great Barrier Reef, where we have really quite good data from the ongoing projects we have there. So just to give you a lesson, we've got about 10% of the Great Barrier Reef covered in seagrass, around about 40,000 square kilometres. I've taken out the line that says we have more seagrass than coral, but it's true. I'm not talking close enough to the mic, so I don't want to fall off the edge of the stage and join your blue profile. So high diversity, 15 species. This is Green Island here. People go to Green Island to look at coral, but you should really go to Green Island and look at the seagrass. There's magic seagrass in Green Island. I just want to put in this graph though to let you know, this is leaf life in days from 0 to 60, and these are just the species we get in the tropics. And note that the average leaf life is less than a fortnight, so if you stick a staple in a seagrass leaf and come back in a fortnight's time, you'll have lost your staple. It'll have grown out of the leaf. These leaf turnover times are really quite high. There's high levels of productivity in the reef waters. So different from down south. And if you look at just the sorts of seagrass you get, and you can get these really dense, seagrass meadows like up in Green Island, or typically Bowling Green Bay, very low density seagrasses. In the deep water you can get quite large seagrass. This is around about 50 metres deep. The seagrass in the reef goes down to about 67 metres. So a variety of different species. When you see someone say there's a trend in seagrass in the Great Barrier Reef, seagrasses are doing this or doing that, understand the nuances behind that we're actually amortising into that sort of statement. A variety of different plant structures, different lifestyles, different life regimes, big species, small species, colonising species and foundation species. Two, these are flowering plants. There's this flower there you can see on that spinulosa, and they produce seeds. Almost none of the seeds are buoyant in tropical seagrasses, so they fall exactly where the plant is or within a couple of 100 metres. It's quite an interesting strategy for a plant because it means your seeds are definitely going somewhere where you're going to get seagrass growth because the seagrass is already there. But it makes it difficult for seeds to be a way of seagrasses recolonising places that have been damaged, say after a cyclone. So interesting strategies there. I just want to mention too that the different seagrasses have different strategies. So a seagrass like Colophila produces 2 little leaves on a petiole at each node. If a dugong comes along and eats that leaf, that plant can't replace it. It has to actually run a rhizome out, produce another 2 leaves somewhere else. This means the plant copes by from herbivory by actually spreading and producing new rhizomes and new leaves. In contrast, a plant like this one, if you eat the leaf off, it can just grow new leaves in situ. It doesn't have to move, it can actually keep producing. And add to that, species like this one down here, with their leaflets like this, can actually increase the leaf size if the light regime drops off. They can add leaflets to the leaf after it's been produced. So these are very different strategies for dealing with loss of light for herbivory. And when we're just doing these very general summaries, we often put them together and just say seagrasses are doing this or seagrasses are doing that, missing some of those nuances which I think we should know about. Added to that, we have these really high levels of herbivory in North Queensland. We have turtles and dugongs. Now Abby just sent me this picture from Green Island. She's doing some caging work on Green Island. She caged some seagrass and the turtles came along and ate around it, leaving their cage with plenty of seagrass. That's a very extreme example of herbivory. But understand when we use metrics like biomass that we're integrating some pretty interesting ecological functions in that, including herbivory, including dieback, leaf loss, etc. And then when I was down in Adelaide the other day, I took a picture of the nice seagrass rack on the beach, Marina Cove. Now this cliffs of seagrass 2 metres high. You can come to North Queensland and look for that on the beach, but it doesn't really rate in terms of rack on the beach. I went down to Rose Bay this morning. It looks much like that. There's heaps of seagrass out there, but it doesn't turn up on the beach like it does in southern Australia. The tropical species, even though they have high leaf growth and high productivity, aren't turning up on the beach in rack. They're being eaten, they're deteriorating because the water's warmer, or being absorbed into the carbon at the bottom. But they're very, very different processes going on. So that was the quick lesson. Now to go to where we are. Well, I said that one of the really useful things about the GBR is that we've had that research program going for since the early 1980s, and NESP round one gave us some dollars to put together all the spatial information we had from that 30, 40 years of sampling. So we now have a layer, and this is just presence absence, and this is publicly available. It's on the Atlas website. Alex is here. Alex was the leader of this group over here. This is just simple presence absence. So where it's green, the seagrass. Where it's white, there wasn't. There's 65,000 records in that database. Again, one of the advantages we have is that we still have at least 3 people from those original 1980 surveys still in the business, so we can go back and verify some of the data that was collected back then, ask questions about how good it was, where it was, what sort of species we really did see. So we're able to go back and validate that data using the NESP project, and that gives us a really good layer of seagrass in the Great Barrier Reef. Now, some of those programs are actually collected randomly or with a semi-random process. So that the 1994 deep water seagrass was random, and there were random processes in the CSRO Seabed Biodiversity Project, which is also in this database. So we have a really good tool there, and that and its precursor have been used in our research team to look at just where the seagrass is and how it's going. And Alex and Kath are going to be talking a little bit more about this, because we have a new NESP project now looking at that data and you can use it. It's searchable through time as well as through space. So to go to the monitoring programs, and we have 2 major monitoring programs in the Great Barrier Reef. There's the Marine Monitoring Program that Len McKenzie runs. I've just pulled out one graph here of biomass to take you through. Jumping ahead. There's 29 sites it's collected from. Those sites have increased through time. There was a little bit of criticism that they were more focused on the southern reef than the northern reef, and we've been adding some reefs in the northern part in recent times, seagrass meadows in the northern part in recent times. But just to put that in a graphic form then, so like I said, we've been adding sites. So you can see the fewer sites back before 2004. We added some sites in 2012 in North Queensland. But if you just put it all together, you can see it follows probably a predictable trend, dropping away after the big cyclone events and then slowly recovering. Katerina was probably correct for seagrass as well as corals, that it's very much the stream flow and water quality, water clarity that affects the seagrass, not just the cyclone event itself. The cyclone event itself is more focused, but following that, the rainfall means you get a recovery. It's really slow. We're looking at around about 3 to 5 year recoveries after a major loss, so that's amortised into this data as well. The other major project is run by Michael Rashid, and that's looking at the port changes in ports. I've just put this into the report card format, but we have a project of monitoring seagrass in every port in Queensland. We use a much more complex process to rank and rate the seagrass in ports, because they're smaller spatial scales and we're able to do much more detailed work. We can do complete mapping, we can do some fairly intense work, and we have some very long data sets going back 20 years. So we've looked at things like using a baseline of 10 years of data from back when we started sampling. You can, I'm not going to go to any details on this, you can look at it yourself if you want to. Each one of these ports has a report and they're on the Topwater website. Interesting to note though that the Gulf ports, while the processes are the same, they're still dredging, they're still running the ports. The seagrass in those meadows is remaining in good condition compared with the east coast, and mainly because they've been spared the big cyclones. If we go to a specific port, and I've just gone to Cairns, and that data set starts in 2001, goes through till last year, and you can see the colours in the slide I just showed you come from the analysis we do in the ports, and you can see how, in this case, just mapped area in the port has tracked from being reasonably good up to very good in the 2009, 2007, and then dropped away under the effects of Cyclone Yassi and Larry, and looking at around about that 3 to 4 to 5 year recovery rate once those cyclones have gone through. So that seems to be pretty constant, that once you lose seagrass, it takes a while to come back, and looking around about that time. So just then to go on to our research projects, the risk mapping, we've worked extensively in ports. The port has some effect on seagrass. Alana and I, when Alana was doing a PhD, Alana Gretsch, who's now with the Centre of Excellence, we mapped out the risks of seagrass to see just how important things like ports were. We did a couple of interesting exercises. We asked the global community to rank risk to seagrass globally from what they knew. And then we went back later and asked them to rank it again based on a set of metrics, things like scale, repeatability, resistance, how many species were involved, and got quite a different answer. When we asked people what they thought, they said, oh, ports and trawling were important. When we did it systematically, the answer was much more focused towards things like water quality, the broader scale issues that were quite repetitive in places like the GBR are much more important. But Alana and I mapped those risks out, and we did it in a Rubik's Cube form here. So down the coast, where it's light blue, there's not much risk and not much seagrass. Where it's dark blue, there's lots of seagrass and not much risk. Where it's red, there's seagrass and risk. And we mapped that out, and the key finding there was that the risks are very much down southern part of the Great Barrier Reef. When you get north of Cairns, the risks are quite low, even though there's plenty of seagrass. Some times, and this is around the Townsville region. Townsville's there somewhere. Townsville, where are we? Here. Around the Townsville region, we were able to model out how seagrass propagules in the water might move. So even though I said the seeds aren't buoyant, the seeds don't float, propagules of seagrass do get around in fragment terms. So you can go out any day and collect these from the surface of the water or just under the water. Fragments of seagrass with growing tips and roots and rhizomes floating in the water. The literature suggests they're probably viable for about 8 weeks in the tropics, possibly slightly less. We used 8 weeks in the model. So what we did was we looked at whether those sort of particles were released from around Townsville, just how far they'd spread. So if we lost seagrass in a cyclone or from water quality, just how easy would it be for that meadow to recover from propagules floating in the water? And we released around about 11 million propagules, 34 different simulations, some on the surface, some in the water column. The answer was quite surprising to us. I mean, it both reaffirmed what we knew, that if you look at the medians there, they're around about sub 100 kilometres. So that the seagrass propagules in general didn't move that far. If you look at the outliers though, the propagules from Townsville could reach the Torres Straits. So there's quite a lot of potential, at least for high levels of dispersibility in the seagrass. It's not quite as simple as it looks though. If you notice some of those sites, and I haven't got a link to sites for this particular talk, but some of those sites, the propagules move much further than others, and that had to do with topography. It was also very, very much a south to north movement and inshore. So we were left wondering after that analysis whether activities that occur in the southern part of the Great Barrier Reef, where most of the impacts are, could be accidentally affecting the much more pristine and low-risk areas to the north, and there were some management implications for that. So the team then went and looked in more detail at how those meadows might be connected, and I can't go into great information here, but so we did a graph analysis, a network analysis based in the Townsville region, using that data, using the hydrodynamic model, and we looked at those metrics of connectivity. The bigger the circle, the more between centrality, the more connected in the model a meadow is. These represent meadows. The meadows are up here. I've got the numbers on them. Offshore meadows, and we're able to look at how those seagrass meadows in an area like Townsville interact together. And the answer was that it's really working as a small network, a very, very highly connected network, and some meadows are very much embedded in it. So meadows such as Cleveland Bay, right here, are highly connected in the network and very important stepping stones through that model. Other meadows were outside the network a little bit, so with high levels of outflux of propagules, but high levels of retention, so not well connected in the model. If one of those meadows was lost in a cyclone, it may not come back easily without some intervention. So this enabled us to look at each meadow as it was in the network, and whether if you lost it, it would likely come back from its own, from natural processes, or would need some help from outside. It also enabled us to more scarily look at meadows like Abbott Point to see how well they're connected in the model, and what would happen if you took a meadow such as Abbott Point out of the model, how that would affect the resilience of other seagrass meadows, because the network showed that if you do damage one meadow in the network, that then spirals through the network and can affect the resilience of other meadows nearby. We haven't published that yet, mainly because given some of the controversies over reports, we've gone back and checked our maths before we submitted for publication, as you would expect. To add to that then, we also looked at how the seagrass meadows, might interact with the animals that feed on them. And Sam Toll and I spent several months running around chasing dugongs and turtles collecting poos, as you can see from the slide. Yes, that's what it is, turtle poo. I've only put the dugong data up here, but Sam showed that from turtle and dugong poo, from around about I think it's gram dry weight of dugong poo, you were getting an average of 1 to 2 seagrass seeds, which about 10% were viable. So just for dugong, on any one night, you can have anywhere from 600 to 4,000 viable seeds being transmitted in dugong poo. You literally sift through that dugong poo looking for seeds, some of which are microscopic, so quite brave. There were 4 species in it, and if you put turtles and dugongs together, on any one night in the Great Barrier Reef, there's around about 500,000 potentially viable seagrass seeds being shifted around by turtles and dugongs. Now, this makes a modelling problem for us, because it's quite hard to model what turtles and dugongs do. They don't just float around in the water, they do their own thing. Some of them move big distances. Sam's put up there around about 234 kilometres, but we can't make turtles do those distances. They make up their own minds. We're still working around that. But clearly there's a very, very close relationship between these animals and seagrass meadows. They go to places where seagrasses like to be, so they're not random at all. And it just underscores how much we're learning through these various programs. And then just to finish, one of the original reasons for being a seagrass group was because we were working on the values of seagrass to the fishing industry. The fishing industry paid for most of the initial surveys. So Paul York and I just stepped back and said, let's ask some questions again, because we now have a very good data set from Trinity Inlet, and Cyclone Yazzie and Larry clearly got rid of the seagrass for a time from Cairns Harbour. We have those maps out there, so those 2 yellow sites are where we sampled back in the 90s. Reg Watson and I and the team actually valued the seagrass based on a model we had back then, one of the few studies that has done that. And we're able to now go back and compare when the seagrass disappeared. So we went out, Paul and I, and trawled on the now absent seagrass. So I've just put it in 3 forms here. So back in 1993, the abundances of prawns around about 25 prawns per trawl. Now, when there was no seagrass there, it's started to cover since then, but when there was no seagrass there, very few prawns, very few species, and we can now work out a yield rate from that meadow, which we're working with Reg Watson with now. So we'll be able to put that value back to the seagrass. I mean, if you work on coral, you don't have to worry about the value of coral. Everyone knows it's valuable. When you work on seagrass, it is important to underscore it by pointing out that we do make our money from these meadows, not just tourists. And just to finish off then, Tropwater has a very extensive website. Tropwater.com will get it if you put that in your browser. You can click on any of those buttons. Most of the research I've talked about today, apart from the stuff on network analysis, is available as published work. Thank you.